Next, we're going to talk about alkane structures. How do we name alkanes? That would be their nomenclature. What kind of physical properties do they have? What kind of shapes do they have? That sort of thing. We'll start with the nomenclature of alkanes. And unfortunately, this is the one part of organic chemistry where you can't avoid doing some memorization, because just like we have to memorize the alphabet in order to learn how to spell and communicate with the written language, we need to know the names of organic molecules if we are to communicate about them. So I've shown here the first 10 alkanes, C1 through C10, and these 10 names you will most definitely need to commit to memory, and so this is maybe a good time for some flashcards and some practice. But of course, the more you practice with these are going to be become second nature to you, much like the alphabet is to you. So the very simplest alkane with one carbon is called methane, 2 carbons is ethane, propane, butane. Pentane is the 5 carbon, just like a pentagon has 5 sides, so that prefix isn't too hard to know. Same with hexane, just like a hexagon. Hexane has 6 carbons, heptane has 7, octane has 8 carbons, just like the octopus, or the octagon has 8 sides or 8 legs. Nonane is 9, and decane is 10. Again, that's a pretty easy one to remember since a decade is 10 years. So out of these 10 that you, at least these 10 you'll need to know. Some of them are quite easy, and others you'll become quickly familiar with as you start working with them. Now, what we're going to find when we go to name an alkane is we're going to first identify a parent carbon chain, and we're going to give that parent carbon chain one of these names: methane, propane, decane, and so on. Attached to that carbon chain are going to be additional groups. We can call those substituents because they are substituted onto the carbon chain. If one of those substituents is another carbon chain, we're going to name that substituent with the same sort of nomenclature, but we're going to replace, instead of having an ANE ending like we do for our parent chain, we're going to have a YL ending. So a 1 carbon group is called a methyl group. 3 carbons is called a propyl group. 2 carbons is called an ethyl, and we could have hexyl and octyl and so on. It's also common to have halogens attached to our alkanes, so let's talk about that nomenclature as well. We're going to add an O, use an O suffix for these groups, so a fluoro, chloro, bromo, iodo is what we call it when there's a halogen attached. And it's also quite common to find a benzene ring attached to a parent chain. Whenever we encounter that, we're going to call that a phenyl group, so that's good to know as well. So the rules we're going to follow in doing our nomenclature is the very first thing is we're going to inspect the structure and identify the longest carbon chain. If we have more than one choice, we're going to identify the one with the maximum number of substituents, and we're going to name that parent, again, using one of these names shown: propane, butane, and so on. The next thing we need to do is we need to number the carbon chain. And we're going to, we have to number from one end or the other, and we're going to choose the end that's closest to the first substituent. And then we're going to name and number the substituents that are attached. We're going to see how you can use prefixes like di and tri and tetra and so on in just a moment. And finally, we're going to alphabetize all of our substituent names and list them out in front to come up with a complete IUPAC name. IUPAC stands for the International Union of Pure and Applied Chemists. This is the committee that has developed these names, and the beauty of nomenclature for organic chemistry, although it might not be the most exciting subject in the world, is that all around the world, all chemists use this same nomenclature rules. So whether you are English speaking or not, when you see this molecule and you follow these same systematic rules, every person around the world should come up with the same name for that molecule. So that's what makes it a very important thing to know. So for example, we could look at this a very simple example. We have a 3 carbon chain. So a 3 carbon chain is going to be called a propane. And but it's not just propane, right? Because we have this chlorine attached to it. and we need to figure out where it's attached. The way we're going to do that is we're going to number the carbon chain. In this case, it doesn't matter which end we start numbering from. We'll get the same result, 1, 2, 3. We see that the chlorine is on the second carbon, so we're going to call this a 2-chloropropane. And this all becomes all one word. There's no space here. We're going to put a dash in between numbers and letters. So this molecule is called 2-chloropropane. How about the next one? Our first step is to find the longest carbon chain. So I see a 1, 2, 3, 4 carbon chain here. And then so this is going to be a butane derivative. And then we need to number the chain. If we numbered from this end, 1, 2, 3, our substituent would be on the third carbon. If we numbered from this end, 1, 2, our substituent would be on the second carbon. So we're going to number it in such a way to give the substituents the lowest possible numbers. And what do we have attached? Sometimes it's really useful to kind of put a box around or a circle around your parent chain so you remember which carbons you've accounted for just by naming the parent. We now have an additional carbon off of carbon 2, and we're not going to call that a methane group. There's no such thing. We call it a methyl group. We use the YL. So we have a 2-methyl butane is the name of the structure, 2-methyl butane. The next one's a little more challenging because we have to search for our longest carbon chain. If we look straight across, 1, 2, 3, 4, we would find a 4-carbon chain. But if we follow a different path and go up here, we see that we can come up with a longer carbon chain. So remember, a molecule can be drawn in any way, so you want to look very closely to find the longest continuous carbon chain. And as long as you're still connecting to another carbon, you don't stop until you hit an end, a carbon that has no other carbons attached. So let's see, this is 1, 2, 3, 4, 5, 6 carbons. So this is a hexane derivative. And we need to number those carbons. We can either start from this end or start from this end. But because this is closer to the first group, we would get a group of carbon number 2. We'll number from there. 1, 2, 3, 4, 5, 6. And again, we have methyl here. We have 2 methyls. We have a methyl on carbon 2 and a methyl on carbon 3. But rather than list those repeating substituents separately, our names would get very long and very cumbersome. What we do is we take the common substituents and we group them together, and we call it instead a dimethyl. And what we do is we list where do those 2 methyls occur. One is a carbon 2, one is a carbon 3, so we call it a 2,3 dimethyl. 2,3 dimethyl hexane. And now we're going to put a comma in between numbers, just like you would if you write the number, 1,000 or 1,000,000. Put a comma between numbers and always a dash between numbers and letters. Now these rules are using the IUPAC nomenclature. In addition to the IUPAC rules, there are a small number of very commonly used names for commonly seen groups, and we do need to be familiar with these as well. So, for example, if you think about a 3-carbon chain that you want to attach to a parent, there's 2 possible points of attachment. You can either attach it from one of the end carbons. So you would end up, if this is your parent, you would have a CH2, CH2, CH3 substituent. We call that a propyl group. And in its common name, it's called an N-propyl just because it's a normal propyl. It's a normal straight chain carbon. If you attached at the middle carbon instead, the group that you've attached would be a CH with 2 CH3s on it. And this is a different arrangement. This is an isomer of the original arrangement. So we call this isopropyl. And you may have heard of the word isopropyl when something like isopropyl alcohol is an astringent you might find in your medicine cabinet. And it means that you have an isopropyl group. And if we come back to this first structure, this 2-chloropropane also has an isopropyl group. It's a 3-carbon chain with something attached to to the middle carbon. And so a common name for this compound could be isopropyl chloride. Isopropyl alcohol would have an OH group attached in this position. Okay, so there are a few common names that you will need to be familiar with. Isopropyl is one example. Another commonly encountered substituent is if we had a 4-carbon chain that we wanted to attach. Now again, if we attach just at the first position, so wait, this was the N position, this was the iso position. Here, if we attached at the first carbon, we would have a CH2, CH2, CH3, so just a normal butyl group. So this is called an N-butyl. And if we were to attach at the second carbon, which is described as a secondary carbon because it has 2 carbons attached, we would get the isomer that is known as sec-butyl. So what would that look like? You have 1 carbon. You have a 3-carbon chain, CH, CH2, CH3, with a 1-carbon group attached. So here you see we have a 4-carbon chain that is attached at the second carbon or the secondary carbon of that. This group is known as the sec-butyl group. This is known as the sec-butyl group. So again, you could have sec-butyl alcohol, sec-butyl chloride, and so on. And then finally, if we could have another arrangement of carbons like this of 4 carbons. So these are commonly encountered. If we attach at this middle carbon is described as a tertiary carbon because it has 3 carbon groups attached, and that's where the name tert-butyl comes from. We use the prefix tert to describe 1 carbon with 3 methyl groups attached to it. Now this is still a butyl group because it has 4 total carbons, but we've attached at the middle carbon with this arrangement. This is called tert-butyl. Or you could just call it T-butyl. Sometimes we just use the first letter of the abbreviation, so tert-butyl. And then the last possible arrangement for 4 carbons is if we attached over here. And this one is known as iso, the isobutyl. And so what does that look like? It has a CH2. It has a CH2. And then we have this isopropyl group. So isobutyl is kind of like an isopropyl with an extra carbon. So then we have what we saw for isopropyl. And this is called isobutyl. So just a brief introduction into some common names that we will be encountering when we take a look at a lot of the names that you're going to be encountering throughout your reading. What would we do if we had a slightly more complex structure? And let's take a look at this one. We might have a line drawing. Okay, looks like we have a 1, 2, 3, 4, 5, 6, 7, 8 carbon chain here, and you might be tempted to take that as your parent, but if you look more closely, you see you have a 1, 2, 3, 4, 5, 6, 7, 8 carbon chain in that direction as well. So how do we distinguish between these two? We come back here and we see that if there is a tie between 2 possible carbon chains, we're going to pick the one with the maximum number of substituents. So we're going to take the more complex path here. We're going to take the more complex path to have a simpler name. I got a little messy there. Okay, now we need to number our chain. If we number from this end, we get our first substituent at 2, and then the next one is at 3. If we number from this end, we get our first substituent at 2, and our second substituent at 2. So that's going to be a better choice. So this is carbon number 1, 2, 3, 4, 5, 6, 7, 8. So this looks like an octane derivative. And what does this octane have attached to it? Well, this is where it's very useful to draw a circle around your parent chain, because now you can see all the other groups that you need to account for. We have a chlorine at 7 and a chlorine at 6. We'll combine those together because it's the same group. We have a 6,7 dichloro. We have 2 chloro groups. At carbon 3, we have a 2-carbon chain. A 2-carbon compound is called ethane, so a 2-carbon substituent is called ethyl. So on carbon 3, we have an ethyl. And at carbon 2, we have, what is this sticking out here? It must just be a 1-carbon group. So we have a 1-carbon, we have a methyl here, and a methyl here. Again, this is we have 2 methyls, so we're going to combine them. We're going to call this a 2,2-dimethyl. A 2,2-dimethyl. If you're saying it's a dimethyl, that means you have 2 methyl groups, so there has to be 2 numbers preceding that showing where both those methyls are. Here they happen to be on the same carbon, so we call it a 2,2-dimethyl. Okay, now how do we organize all this information? We're going to just alphabetize it. So we're going to list, when you alphabetize, you ignore the prefixes that you added. So you're going to ignore the di in this case. So the first letter that would come first is the C for chloro. So we would have a 6,7 dichloro. We took care of that one. And then we have an ethyl and a methyl. Ethyl comes first. Then we do a dash 3-ethyl. Took care of that one. Now we have our methyl. So then we go dash 2,2-dimethyl. And then we go right into octane, no space there. So you can see these names can get pretty long pretty quickly. This is called 6,7 dichloro, 3-ethyl, 2,2-dimethyl octane. Let's take a look at the molecular formula that we expect for an alkane, and something known as a degree of unsaturation. A general formula for an alkane is C to the N, H to the 2N plus 2. If we have that formula, we describe that as being a saturated hydrocarbon. That means we have the maximum number of hydrogens. So being saturated describes the relationship. It's saturated with hydrogen atoms. Okay, so for example, if we have heptane, if using this formula, we could determine the molecular formula for heptane. Heptane means that we have 7 carbons. And so how many hydrogens are there? Must be 2N plus 2. So 2N is 14 plus 2. So the formula for heptane is C7H16. So that's another very good formula to know, C to the N, H to the 2N plus 2. That's going to come in handy. Okay, why does it always end up being 2N plus 2? Well, let's take a look at just a regular carbon chain. And let's think about how many hydrogens this carbon chain is going to require. We know that a carbon's going to want 4 bonds. So every one of these carbons has 2 hydrogens. So you'll see that we always have twice the number of hydrogens as we do carbons. But this structure isn't complete, is it? At the end, we need to cap it off with a hydrogen on each end, and that's where we get our plus 2. 2N plus 2. And it turns out no matter how I arrange these carbons, or if I had 10 carbons and put them all different connectivity, we're always going to have that same number of hydrogens. What if I wanted to add a ring, however? What if I wanted to connect the ends of these carbons? What would I have to do? I would have to remove a hydrogen here and remove a hydrogen here in order to connect these. So addition of a ring is something that causes me to lose 2 hydrogens. What if I wanted to add a pi bond to this structure? Again, in order to form a double bond here, I'd have to remove a hydrogen from each carbon And so the addition of a pi bond also causes the loss of 2 missing hydrogens. So when we inspect a formula and we identify that there are 2 missing hydrogens, that gives us an important clue. And every 2 missing hydrogens is called a degree or a site of unsaturation. We would describe that as having 1 du if a formula had 2 missing hydrogens. So for example, let's take a look at the formula C9H16 and ask how many degrees of unsaturation there are. Okay, and a lot of textbooks have some pretty complicated formulas for these, and really the only formula you ever need to know is this one right here. As long as you know this formula, doing these types of problems is very straightforward. The question you ask yourself is, if it was saturated, what would the formula be? Well, there's 9 carbons, so how many hydrogens does that require? 2n plus 2. So 9 times 2 is 18, plus 2 is 20. There's our 9 times 2 plus 2. Okay, so if it was saturated, our formula should be C9H20, but it's not. It's actually C9H16. So all we need to do, very simply, is compare those two formula, and what do we find? There are 4 hydrogens missing. Because every 2 missing hydrogens is 1 degree of unsaturation, 4 missing hydrogens means we have 2 degrees of unsaturation. Let's try another one. How do we determine the degrees of unsaturation if our formula contains something other than carbons or hydrogens? Okay, well, how about a halogen? If I wanted to put a halogen on this structure, what would I have to do? I would have to remove one of the hydrogens and put a halogen in its place, because just like hydrogen, halogens require just 1 sigma bond. And so every time we see a halogen, we're going to count as a hydrogen. We're going to count it as if it were a hydrogen, because they take the same place. If we see an oxygen in the formula, we get to ignore these. It turns out that adding an oxygen to this structure has no effect on the number of hydrogens. And if you think about an oxygen, can form 2 bonds. So if I wanted to put in an oxygen here, I would just kind of squeeze it in between one of the bonds that are already here, and I would not have to replace any hydrogens. So we get to ignore the oxygen, and so that means this formula is the equivalent of having C6H12, because we dropped the oxygen and we included the chlorine with our hydrogen count. And now we proceed as usual. What do? We ask, if it was saturated, what would the formula be? For 6 carbons, we need 14 hydrogens, 2n plus 2. We compare that to the actual formula, C6H12, and we see that there are 2 missing hydrogens. Does that mean we have 2 degrees of unsaturation? No, every 2 hydrogens missing is 1 du. Okay, so that's how we can work with the formula of an alkane or a related compound to determine unsaturation. And you can even look at a structure and determine the degrees of unsaturation. So without considering the formula, just let's take a look at the structure of benzene and determine how many degrees of unsaturation are there. Well, a degree of unsaturation is defined as either a ring or a pi bond, because those are the structural units that cause hydrogen to be missing. So what does benzene have? It has 1 ring plus 1, 2, 3 pi bonds. So it must have 4 du. So determining degrees of unsaturation given a structure is very simple. We just count up the rings and the pi bonds. If you wanted to check the formula and practice your calculation there and confirm that based on the formula you would also determine that it is 4 du, the benzene formula is C6H6. Each of these carbons has just 1 hydrogen attached. So it's C6H6, and if you do your calculation, you should come up again with 4 du for benzene. Now, one way that understanding these degrees of unsaturation can be very helpful is if you have an exercise such as the one shown here. if I asked you to draw the isomers as C5H12, the very first thing you should do is calculate the DU. That's going to tell you something about the structure. So let's do that. If it was saturated, what would the formula be? For 5 carbons, we need 2N plus 2, we need 12 hydrogens. And guess what? Our structure has all 12 hydrogens, so that means there are 0 DU. There are no degrees of unsaturation. So what clue does that give us about our structure? It tells us that all isomers of formula C5H12 can have no rings and they can have no pi bonds. No rings and no pi bonds. Because those structural elements would not allow 12 hydrogens to fit onto the structure. Okay? This frees us from ever having to count the hydrogens in our structure. All we have to worry about now are the carbons. So let's deal with our 5 carbons. How can we put them together? One way is to connect them all in a straight line. Okay, this would be one isomer of C5H12. I know that when I fill in the hydrogens, I'll have 12. I don't need to do that initially while I'm working this problem. Now a systematic way of approaching the problem would be to say, okay, well, how about having a 4-carbon chain and then taking that one extra carbon and attaching it somewhere on that chain. So what if I attached it to this first carbon? What do you think about that? Does that look like a new isomer of C5H12? Well, no, because this is really the same structure I've drawn. It's still a 5 carbons all in a line. Just because I've drawn it differently on the page doesn't mean it's something new. So that's something you're really going to have to be on the lookout for when you're drawing isomers, that you don't have any repeat structures. Okay, but if I had 4 carbons and I attached it to the second carbon, that would be a unique carbon chain from this. So that would be a new isomer. Again, I'm guaranteed that they would have 12 hydrogens when I fill in all the hydrogens. Okay, how about 4 carbons and then I move it over to the third carbon, that extra carbon? Wow, that looks like it's a repeat of this again, right? All I did was flip the molecule over. Now this is where understanding nomenclature can come in handy, because these both would have the same name. This would be 2-methyl-butane. This would be 2-methyl-butane. So checking the name of a compound is a great way to determine whether you've drawn a repeat or not. So how about going to a 3-carbon chain and having 2 extra carbons to work with? Well, I could maybe put one here and put one here. There's 5 carbons. Do you think that's something new? Or do we still have a 4-carbon chain with an extra carbon on the second carbon? Still 2-methylbutane. 3 carbons, and maybe I can do it as a 2-carbon chain? Nope, still 4-carbon chain. So it's going to be, you're really going to have to look very closely. The last arrangement we can have is having the 3 carbons and then putting both carbons on the middle carbon. This now would be a unique arrangement of the carbon atoms. So it's just these 3 possible isomers. There are 3 isomers. They are all C5H12. I was able to do this problem so much more quickly by just thinking about degrees of unsaturation and not ever counting up my hydrogens. And you can go ahead and fill in those hydrogens and convince yourself that you have 12. Okay? But what I know immediately is that I don't have to consider a structure like this. How about if I put the 5 carbons in a ring? Could that be one of my isomers? It can't be, because it has a ring, and that means it's going to be not C5H12, it's going to be C5H10, because putting in a ring causes us to lose 2 hydrogens. So very useful to know this technique when you're working on isomer problems. Let's talk about how alkanes will behave. What sort of physical properties would they have? Alkanes just have carbons and hydrogens, so they are going to be nonpolar molecules. That makes them not very soluble in water, not at all soluble in water, because water is a very polar molecule, and we know like dissolves like. So we could describe alkanes as being hydrophobic. as being hydrophobic because they have very poor interactions with water. They are isolated from petroleum reserves. Crude oil, part of the distillation process in the refinery, separates out the alkanes based on their boiling points, and so this is where we get our alkanes commercially. And it turns out that alkanes are fairly unreactive. Remember, these have all strong sigma bonds. An alkane can't have any pi bonds. It has no other atoms in there other than carbon and hydrogen. So because it has no pi bonds and it has no lone pairs, there really aren't too many reactions that they're going to want to undergo. There are a few exceptions. One reaction is that alkanes can be used as fuel. So in other words, they can undergo combustion. And that, of course, is what we do with many of the alkanes we get from crude oil. So if you looked at the names, butane, propane is the fuel we use for our gas barbecues. Methane is the fuel we use to heat our homes. Butane are for disposable lighters. Octane is a component in gasoline. So we might be familiar with many of these alkanes in our everyday lives because of their role as being a fuel. There is a single reaction that alkanes can undergo that we typically study in organic chemistry, is called a halogenation reaction, and that's where we take an alkane and we convert it to an alkyl halide. So we replace one of the hydrogens of the alkane with a halogen like chlorine or bromine, and that is one of the reactions we'll be studying for alkanes in just a bit. And let's talk about their physical properties. Here we have a series of alkanes. We have a 3-carbon chain, and then a 6-carbon chain, and then a 31-carbon chain. So what do we expect? What do we observe happening here? We see an increase in our boiling points. If you have a boiling point of minus 42 degrees, that means it's going to be a gas at room temperature. So room temperature is somewhere around 20 degrees C. So this is going to go to a liquid form all the way down at minus 42. This 3-carbon chain is propane, and we know propane is a gas. That makes sense. When we have 6-carbon chains, we now have a boiling point of 69. So hexane is a liquid that is can be used as a solvent. Again, components in gasoline, we have hexanes in there. So that is a liquid. And when you have a boiling point above 300 degrees, that means it's going to be very hard even to melt it and then to boil it. This is solid. It's a waxy solid. Kind of like beeswax or candle wax might have a formula like this. Very, very long carbon chains, completely hydrophobic, greasy, waxy, that sort of thing. And so what is the trend here? What explains this increase in boiling points? Well, simply as we increase our molecular weight, they all have the same polarity, of course. They're all nonpolar. But as you increase your molecular weight, you increase your surface area, you increase your van der Waals attractions or London forces, and that's going to increase your boiling point. So the trends we saw in looking at the various intermolecular non-bonding interactions. And how about the shape of alkanes? What do they look like in 3 dimensions? We can have different shapes known as conformational isomers. I put isomers in quotes here because these are not isomers in the traditional sense of isomers that are non-interconvertible unique compounds. Conformational isomers, also called conformers, are actually can be interconverted, and so that's why I prefer not to call them isomers. I prefer to call them conformers instead. And the way they are related is they are structures which differ only by rotation about sigma bonds. Okay, so conformers are different forms of the same molecule. And they are interconvertible because the way we go from one to the other is simply by rotation around a sigma bond. So for example, conformations of ethane, if we take a look at an ethane molecule, We have just a 2-carbon structure, CH, this is a CH3, 1, 2, 3, this is a CH3. The various conformations that ethane can have are these. We can simply rotate around this carbon-carbon bond, and in doing so, this molecule is going to have a different three-dimensional shape. And the relationship of, let's say, this conformer to this conformer they're called conformational isomers or conformers. And so I have shown here examples of 2 extreme conformations. One conformation has 2 hydrogens pointing up in the same direction. And if we rotate this just 60 degrees, we'll see in our 3D sketch that one hydrogen is pointing up and one is pointing down. Or we can rotate it this way and get that same conformation where one hydrogen is up and one hydrogen is down. We have names for these conformations. When the 2 hydrogens in the plane are pointing up, we call this the eclipsed conformation. And when one is up and one is down, we call this the staggered conformation. Okay, and these are rapidly interconverting conformers. So these are not 2 different molecules. It's simply one molecule that's rotating around very rapidly. Now, one way that you can really see why we call these eclipsed and staggered conformations is when we view the molecule not sideways like we did in the 3D sketch, but we view it in this way where we're viewing down the carbon-carbon bond. Okay, and when we do that, now the way we're going to see the eclipsed conformation is when the 3 groups in the front exactly align with the 3 groups in the back. So this has one, straight down, or they both have one straight down, or maybe they both have one straight up. We call this eclipsed conformation, just like a solar eclipse or a lunar eclipse, or when these things line up with one another. Okay, and the staggered conformation is when you have the bonds in the back are kind of intersecting the bonds in the front, and so it goes front, back, and they're staggered that way. This point of view is called a Newman projection. It's a very valuable projection. The way we can see that is by kind of standing over here and viewing the molecule like this, looking down the C2, C3, the carbon-carbon bond. And what do we see on this front carbon? On this front carbon, we see a hydrogen pointing straight up. And then we have hydrogens down. One is to my right. If I'm looking here, the wedged bond is to my right, and the other one is to my left. So this is what we see on the front carbon. And what do you see on the back carbon? Well, the back carbon, you see the exact same thing. There's a hydrogen straight up, and then the other 2 hydrogens are down and to the left and right. Now, the way we show the back carbon in a Newman projection is we draw it as a big circle so that we can see them both. So this is the back carbon, and this dot is the front carbon. And the back carbon in this eclipsed conformation, we recognize that the hydrogen, the back hydrogen, is exactly behind the front hydrogen. But what we do is we tilt it just a little tiny bit so that we can see it, so it's visible. So we in our drawing, we move it slightly, but we keep them very close to each other because we recognize that they are, in fact, exactly aligned. So this is what the eclipsed conformation looks like in a Newman projection. If we rotate the front carbon slightly like we did here, so we rotated around this carbon-carbon bond to get this structure, and now by rotating it 60 degrees, we take this front hydrogen and move it 60 degrees. We do it clockwise. This front hydrogen, all 3 groups rotate as we twist the molecule. Then what happens now is on this front carbon, when we take this same perspective, now on the front carbon we have a hydrogen pointing straight down. And the other 2 are up and to the right and left. On the back carbon, we see a hydrogen pointing straight up. And then the other hydrogens are down and to the right and left. And so here we see the staggered conformation, a little easier to see in this Newman projection. Now, are these conformations equal in energy? They're not. The eclipsed conformation is higher in energy. It is less stable. because of the interactions between the electrons in the CH bond in the front and the CH bonds in the back being perfectly aligned. We get some interactions there. We call that a torsional strain. In having those groups aligned, and when they are spread out, we have a staggered conformation, which is lower in energy. Okay, so while the staggered conformation is lower in energy, again, this is just rapidly rotating, freely rotating around quite easily. Let's call this eclipsed conformation A and the staggered conformation B. And what we can do is we can trace the energy of this molecule as it goes through the various conformations. So if we start with the A conformation, which is staggered, a 60-degree rotation. Again, if we're rotating, it looks like we're rotating this front carbon because the back carbon stays the same. We go from being staggered to being eclipsed. That's structure B. Another 60-degree rotation would bring me right back to another staggered conformation, bring me right back to a conformer that is equivalent to A, and so on. The next rotation brings me back to B, and so on. So if we were to trace our energy curve, at 0 degrees initially, we would be at a staggered conformation that is a low energy conformation. And then after 60 degrees, we will be at a higher energy conformation, the highest energy conformation, in fact, the maximum energy you can have. The least stable is when it's completely eclipsed. But then as you continue rotating, you come back down to your staggered conformation and then back up to eclipsed, down to staggered, and so on. As you rotate, if you were to track just a single hydrogen all the way through 360 degrees, you'd come back to A. And what happens if you trace the energy of this, the staggered is the absolute most stable conformation. As you start to bring those hydrogens closer and closer and closer, they become eclipsed, and then we're at the maximum conformation energy. And then as they slide past one another, then we start to decrease in energy, and we go down to a fully staggered, and so on. We go up to eclipsed, and down to staggered, and up to eclipsed. And this is what our energy diagram looks like as we rotate through the various conformations of ethane. Now, butane is a more interesting molecule because instead of having just 2 carbons and 3 hydrogens on the front carbon and the back carbon, if we take a look at butane, which has 4 carbons, if we again view it as a Newman projection, take a look what's going to happen. As you do your conformations, what you can see pretty quickly is that we have a methyl group on the front carbon and a methyl group on the back carbon, and that relationship of those 2 methyls is continuously changing as we rotate at 360 degrees. So what do you think is going to be the absolute worst conformation of butane to have? Looks like it's probably right here where those 2 methyl groups are exactly aligned to each other. They're eclipsed with each other, and in fact you can even see that they're crashing into each other. We'll talk about that in a second. And what would be the best possible conformation, the lowest energy? It's going to be the one where these large methyl groups are as far apart from each other as possible. So we'll take a look at that as well. So for the Newman projection, what we do for butane, the most interesting point of view is to look down the carbon-carbon bond between the middle 2 carbons. So we call that viewing down the C2-C3 bond. And looking from this perspective, what do we see on the front carbon? We see a methyl group pointing straight up. So we have a methyl group pointing straight up, and we have hydrogens down into our right or left. And what do we see on the back carbon? We see a methyl group going straight down. So this line now is drawn from the circle because the circle represents the back carbon. And then we have a hydrogen up to the right and up and to the left. So this is a Newman projection of butane. If we were to trace the energy as we go from one conformation to the other, let's take a look at the forms that we're going to have. We start out in this first conformation where the methyl groups, first of all, it's a staggered conformation, and the methyl groups are as far apart from each other as possible. When we rotate 60 degrees, okay, what we're going to do here is we're going to rotate the front carbon clockwise. And as usual, that's going to bring us from a staggered conformation to an eclipsed conformation. Continued rotation brings us to the staggered conformation. We see our methyl group traveling down. Now it's going to be eclipsed where it's down at the bottom. Then it's staggered again, and then it's eclipsed. And then our final rotation is going to bring us back to our first structure, A. So our last rotation to get 360 degrees brings us back to A. Now we have names for these staggered conformation when the two methyl groups are as far apart from each other as possible. We call that the anti-conformation. Anti meaning opposite. They're 180 degrees from each other in this dihedral angle. And when the two methyl groups are right next to each other, we call this interaction a gauche interaction. Let me write the name down first. Gauche. And what happens in a gauche interaction is we start to get some interaction between the bulky methyl group on the front carbon and the methyl group on the back carbon. And we describe that interaction as steric hindrance, or just sterics for short. And this is the interaction we have between very large or bulky groups. And it's not a good thing to have large groups near each other. That will cause some instability and this steric hindrance. So a gauche conformation has some steric hindrance. And this is another gauche conformation. When the two methyl groups are on adjacent positions, we describe that as being gauche. There's two gauche conformations. So when we look at our three staggered conformations, A and C and E, what's going to be the most stable conformation? The best one is going to be the anti, where the methyl groups are as far apart from each other as possible. So let's put that on the lowest possible level. And then when we come over to C, if we imagine this A level here, this energy level, when we come over to C, we expect that to be, because there has some steric hindrance, we expect this to be a little higher in energy than A. And E has the same exact gauche interaction that C does, so E is going to be at the same energy as C. And then when we go 360 degrees, we come all the way back to A. That's full circle. Now let's compare our eclipsed conformations. Our eclipsed conformations are all going to be bad, but which one's the worst? Here we have two interactions of methyls with hydrogens. Here we have an interaction between two methyls. When our two largest groups are eclipsing each other, that has the worst sterics. And that's going to be the highest energy eclipse. We said that the staggered, we should mention that up here, is the lowest energy. So when we come to when we come to B, it's going to be a high energy conformation. But when we get to D, the eclipse one, it's going to be the highest energy. We're going to put that up, the least stable. We're going to put this all the way up here. And then when we come to our final eclipse structure, F, it has the same interactions that B does, the methyls with the hydrogens. So we're going to put that at the same level, exact same energy as B. So B, energy of B equals F. These are the two eclipse conformations with equal energy. And the energy of C is equal to E. Those have equal energies as well. And now when we connect when we follow the energy path, we're going to go up to an eclipse conformation, back down to a staggered, up to the worst eclipsed, down to a staggered, up to eclipsed, and back down to the most stable conformation. And when we follow this path with our model, we're starting with the front methyl group straight up and the back methyl group straight down. And then we're going to be rotating this clockwise. So we're going to go up in energy to an eclipsed, and then back down in energy to a staggered. But this staggered is not going to be as good because we have this gauche interaction. We have a little steric interaction between these two methyls. Then we're going to continue and we're going to go up in energy to the highest eclipsed, because we have these two methyl groups interacting with steric hindrance, so that's the worst. But as they swing past each other, we go back down to a staggered, and then back up to an eclipsed, and then back up to our best staggered. So we're always going to be alternating energy between maxima and minima. So what you can see, what's real important is to note that all eclipsed conformations are high energy. Even the best eclipse is still bad compared to any of the staggereds. And all the staggered ones are low energy. So these are some things to point out. And you also want to keep in mind that there's a significant difference between the eclipsed ones and the staggered ones. The difference between the staggered, the various eclipsed conformations is on the order of 1 kcal, where the difference in energy between the worst eclipsed and the best staggered is about 5 kcal. And likewise, the difference between the gauche and the anti is somewhere around 1 kcal. So not a huge difference between the staggered energies or between the eclipsed energies, but between the staggered and eclipsed, that's where you want to see the biggest jump when you're trying to do these sorts of energy diagrams for conformations. If we take a look at cycloalkanes, when we try and form a ring, and we try and do it with either a 3-carbon chain or a 4-carbon chain, and we try and form it into a ring, even with this model, you can see that we're meeting some resistance. That's not an easy thing to do. In fact, that's a good way to break a model kit. And the problem is that if we were to try and form a triangle, a cyclopropane, this bond angle would have to be 60 degrees in order to be a triangle, and it's very difficult for it to make that. Carbon wants to be 109.5 because it's sp3 hybridized, and it can't do that. And even with a cyclobutane, this would require a 90-degree angle, and that would also compress that angle together. We describe that strain as angle strain. In addition, when you take a look at the structures, if you do form this and you look at the Newman projection, you see that the front hydrogens exactly line up with the back hydrogens. We call those eclipsing each other, and we describe that as torsional strain. And there's no way to alleviate that. Unlike the regular butane, where we could rotate in various conformations, this is locked into this rigid structure, and so there's no way to get around that. So when you take a look at cyclopropane, you have this wedge and dash hydrogen and this wedge and dash hydrogen, and they are all eclipsing each other. And so that offers some torsional strain as well. So both cyclopropane and cyclobutane are unstable molecules. And together we describe this combination of torsional strain and angle strain as having a high amount of ring strain. We call it ring strain when we try and form these small rings of 3 and 4 members. So it's possible that these compounds do exist, but they're very high energy. They're highly reactive and difficult to form. When you form a 5-membered ring, however, it's going to be easier to bring these together because we have more room. And you can see, actually, even with this model kit, it's quite easy to bring these ends together and connect it. So this has very little strain. The angles can naturally be very close to 109.5. And if we were to hold the molecule completely planar, then we would have this eclipsing interaction again with the front and the back. But if we bend the molecule slightly, we can alleviate some of that torsional strain and get some better interactions. And so this conformation is known as the envelope conformation, where you have 4 carbons in one plane, and then the 5th carbon is bent out of that plane. And that's what cyclopentane looks like. Cyclohexane is a compound that we'll spend quite a bit of time studying, because when you have a 6-membered ring and you bring it together, the structure you end up with has absolutely no ring strain. It's completely flexible. It's just as flexible and just as stable as it would have been if it were in a straight chain. And so 6-membered rings are very common in organic chemistry. What we'll find is that because this can rotate about the sigma bonds, there are various conformations that cyclohexane can have. The 2 extreme conformations are shown in the drawing here. One is called a chair conformation, and that's where you have 4 carbons are in one plane. That's kind of like the seat of the chair, and then you have this carbon pointing up and this carbon pointing down. Okay, or vice versa, you have 4 here and the one on this side is pointing down, the one on this side is pointing up. This is called a chair conformation. The other extreme conformation is where both carbons on either end are pointing in the same direction. So here we have our 4 carbons are in one plane, and then we have this carbon up and this carbon up. This kind of is a boat shape. We call this the boat conformation. Okay, and as shown here with this equilibrium, you can see that it's favoring the direction of the chair. The chair is the more stable conformation, and the boat is less stable. And there are a number of reasons that the boat is less stable. One is that if you look at the hydrogens on these top carbons, you see that they're facing in near one another. And so we have some steric interactions. These are called flagpole hydrogens. So we have some sterics. In addition, if you take a look at the hydrogens on this carbon, these front 2 carbons, you see that these are eclipsing. So we have some torsional strain as well. Okay, in fact, the boat is so unstable that cyclohexane really never hangs out in the boat conformation. What happens instead to alleviate some of these interactions, rather than having these 2 hydrogens pointing in right towards each other, it twists a little bit to avoid that interaction. We call that the twist boat conformation. So you'll see this drawing sometimes as a way to represent something that's not as good as a chair, but not quite as bad as the boat. These 2 conformations are interconverting because we can rotate around, and so the chair kind of goes through a twist boat as it's going to the boat and back to the chair. Now, drawing a cyclohexane chair is going to be a skill that you want to develop in organic chemistry. And let's go through how to do that. The first thing you want to do is draw a wedge, draw a little angle here. And then you're going to draw 2 bonds coming down that are parallel to each other. And then you're going to draw another wedge pointing up. Wherever this bond was drawn, this bond is going to be parallel to that. And however this bond was drawn, you're going to draw a bond parallel to that. So this is the general form that a chair is going to take. Okay, with some practice, you get something good there. What you want to avoid is just kind of drawing a zigzag thing like this, because then it's going to be very hard to show any detail on that chair. Okay, now what you'll notice when you look at a chair conformation, notice that I've put some different colored atoms on this to illustrate the 2 different types of positions you have on a chair. Some of these atoms are pointing straight up. Let me get a good thing. My model's a little too wobbly here. Here you see that the red atoms are pointing straight up and straight down. Okay? Notice that the chair is a zigzag. It goes up, down, up, down, up, down, kind of like we draw our zigzag line drawings. Every carbon that is a zigzag up has a hydrogen atom or a position straight up. Every one that is a zigzag down has one that's going straight down. So these are the first ones we should draw onto our chair. This is a zigzag up, so it has a hydrogen going straight up. This is a zigzag down. It has one going straight down, and then we go up, and then we go down, and notice that they're alternating up and then down, and then the perspective that we take is that this carbon up on the top is behind these carbons in the front. So we're looking at the chair from an angle, and we're tipping it down a little bit so that these front carbons are downward and the back carbons are the ones that are closer to the top of the page. Okay, so we have these 6 positions that are all straight up and down. We call these axial positions, so let's label these as axial hydrogens. 6 that are straight up. I'm sorry, 3 that are straight up and 3 that are straight down. Those are the easiest ones to put on first. Okay, and then on each position, each of these is a CH2, so there's another hydrogen on each of these positions, but take a look at these. These are all pointing to around the, kind of like the equator of the molecule. These are called the equatorial hydrogens. And notice that none of them are, are pointing straight out. They're not at a 90 degree. They're either slightly down or slightly up. Slightly down, slightly up. So when we draw in the equatorial hydrogens, we take a look at the axial we've drawn, and then we know that it's a 109.5 angle, so we draw it slightly down and then slightly up. We could draw these on this end, and then over here we could draw slightly down and then slightly up. And then we have these in the middle as well. This is where we'll draw this equatorial hydrogen, and this is where we'll draw this equatorial hydrogen. Okay, and again, with practice, you'll get better at this. But every bond that you draw, the axials are straight up and down. Every other bond that you draw is going to be parallel to some other bond. So see that this equatorial is parallel to this bond in the cyclohexane. And in a nicely drawn cyclohexane, you'll see that you can see this W here, or you can see an M here. So those are some of the features you can look for as you're drawing it and trying to decide where to put your equatorial and your axial. A Newman projection of a cyclohexane is interesting because as you view down one carbon-carbon bond, you are simultaneously viewing down the parallel carbon-carbon bond. And so if we view the molecule in this direction, looking down this carbon-carbon bond, we're at the same time viewing this carbon-carbon bond. So on this front carbon, I see a hydrogen straight down and a hydrogen up and to my right, and up and to my left I have this CH2. On the back carbon, I have a hydrogen straight up and a hydrogen down and to my left, and down and to my right I have a CH2. So there's our Newman projection of the carbon on the left. The carbon on the right, I see a hydrogen straight down, and then the CH2 up and to my left, that's connecting this CH2. And on the back carbon, we have a hydrogen straight up, hydrogen down and to the right, and down and to the left. I have the CH2 that was down and to the right from the other back carbon. Okay, so a lot to go through pretty quickly, but as you take your time and try it on your own, what this illustrates very nicely is that this is an all staggered conformation. So coming back to why the chair conformation is so stable, not only does it avoid the flagpole hydrogens, but it also avoids the eclipsing interactions that you have with the boat. Everything is very nicely staggered. Now, when you draw a chair conformation or you look at a chair conformation for cyclohexane, what we'll find is that there's actually 2 possible chairs that any cyclohexane derivative can have. Right now, the molecule I have has all the red atoms in the axial position. If I perform a little magic trick here, I can convert it to the conformation where all of the white atoms are in the axial position. What I just did there is called a chair flip, and I've drawn a model here where I have just an X representing the axial positions. what happens in a chair flip is that you take this end carbon and flip it up, and you take the other end carbon and you flip it down. So let's take a look at that with the model. I have this carbon. There's 4 carbons in the middle. That's the seat of my chair. I take the one on the far left that's down, and I bring it up, kind of into a boat conformation temporarily, and then I take the one on the far right and I bring it down, and I have a new chair. So the way we can translate it to the next chair is, let's number our carbons. Let's call this 1, 2, 3, 4. Those are the front carbons. 5, 6. And this carbon that's on the far left is still on the far left. He was pointing down, but now he's pointing up. This is 1. And then because we numbered counterclockwise here, we're going to continue numbering counterclockwise. The front carbons are still in the front. 1, 2, 3, 4, 5, 6. And on carbon 1, the X was in the down position. If you think of a cyclohexane, if you flattened out the ring, totally flatten it out, six of the atoms are pointing up and 6 are pointing down, right? So because he started out in the down position, he's still going to be in the down position. Where is the down position? It's right here. Carbon 2 has an X up. Carbon 2 still has an X up, and they alternated. Down, and then up, down, and then up. And look what happened. All of our axial groups are now equatorial, and all of our equatorial groups have become axial. So this is called a chair flip. And let's see an example of it. Here we have methyl cyclohexane. If we wanted to do a chair flip of methyl cyclohexane, what we would do is we would take this carbon on the left and bring him up, bring the carbon on the right and bring him down, and then the chair that we have can't have the same shape anymore. Instead of starting down and going up, it's going to start up and go down. And then we draw our 2 parallel lines. So this is our new chair. They should have this mirror image relationship to one another. And this carbon on the far right is now this carbon on the far right. The methyl was up. The methyl still is up. Where are the 2 positions on this carbon? Because it is a zigzag down, that means it has an axial straight down and an equatorial straight slightly up. And where does the methyl go? He was up and in the axial position. Now he's up and in the equatorial position. So these are the 2 chair conformations of methyl cyclohexane. Now, the next question we can ask is, are each of these conformations equal in energy? And the answer is no. This is the more stable conformation. And this is the less stable conformation. And that's because the large methyl group has some sterics when it's in the axial position, as it is here. It has steric interactions called 1,4 diaxial interactions. When we have an axial group, it sees these axial hydrogens, and they can crowd each other and have some sterics. So those sterics are called 1,4 diaxial. That makes this less stable. So this equilibrium lies in the direction, in the forward direction here, where the larger group is put in the equatorial position. Let's try just one example of this. How about if we're asked to draw the chair conformations of cis 1-t-butyl-4-methyl cyclohexane? Okay, now cis means that the groups are both up or both down. So let's draw a chair. Let's just draw it flat first. We have, in one position, we have a methyl group. In the other position, we have a tert-butyl group. So just so we get oriented, this is what we're trying to draw. And so we want to draw chair conformations. So let's draw one chair. Okay, and let's Try and straighten out my lines here. Let's make these our end carbons, the opposite carbons here. Here we have a methyl group up. So let's put our methyl group up on this end. And then on the far end, on the fourth carbon, we have a T-butyl group up. Okay, that would be one chair conformation. The other chair conformation, where we bring this down and we bring this up, would look like this. There's our other chair conformation. Now our methyl group is up here in the axial position, and our T-butyl group is up here in the equatorial position. So what if we have to make a choice? We know that large groups prefer to be in the equatorial position, but how do we decide if they can't both be in the equatorial position? It'd be great if they could, but they can't here. Well, because the tert-butyl group is a larger group, the larger group prefers the equatorial. Larger group prefers the equatorial position. So our equilibrium is going to lie in this direction. Remember that the problem with having the larger group in the axial is that this group crowds the other axial groups, the other hydrogens in this case, called 1,4-diaxial interactions. And if you take a look at what a methyl group looks like compared to a tert-butyl group, a tert-butyl group is kind of notorious for being a very, very bulky group. It has 3 methyls attached to a single carbon. So this would have a lot of steric hindrance, where a small methyl group wouldn't mind as much being in the axial position. And we can look at a variety of different substituents and see what their preference is for being in the axial versus equatorial position. A hydrogen, we call this the A value. It's the energy difference between the axial and the equatorial. So of course for a hydrogen there's no difference. A chlorine is slightly larger, so it has a small energy difference. Methyl and ethyl are close to the same. Remember, an ethyl group can kind of just rotate out of the way to avoid this interaction. But when you get to T-butyl, look at this huge number. A T-butyl group is so bulky that it essentially locks. We could say that this is locked in this chair. It's so difficult to flip that T-butyl group up into the axial position. So this is a way to kind of lock a single conformation. One interesting example is, how about this alkyne, this triple bond group? Why is that such a small number? Can you think about the geometry of a triple bond? If I were to put this in an axial position, what is that going to look like? It goes straight up, doesn't it? So how much interaction is going to have with these other axial hydrogens? Not very much compared to a tert-butyl group. Let's put this on here while I have the model. A tert-butyl group in this position, there's no way it can alleviate that steric strain. So there's a very high energy there. So, but this is so small because it is linear. And so when we put that in an axial position, it goes straight up. And there are little steric interactions, very little steric interactions, so it doesn't mind being it. So when we have to make a choice between chair conformations, we're going to pick the one with the largest group in the equatorial position.